Hello and welcome back. I keep looking at the brick wall, and this brick wall is such a beautiful metaphor for quantum physics. Again, at the risk of stating the obvious, we build walls out of bricks. We sum up bricks and we can make arbitrary brick walls. We can also take superpositions of eigenfunctions, our so-called eigenfunction expansion, equation 151. Instead of a brick wall, we can have an arbitrary wave function as a function of position and time, and we can express it as a superposition of a complete set of eigenfunctions, little psi, subscripted with some integer n, some weighting coefficients, complex weighting coefficients, c subscript n, add up something over n, and we have our eigenfunction expansion. And this may or may not have been relevant to the assignment. All right, we want to ask a question about the meaning of these coefficients, C for coefficient, the meaning of these complex coefficients in this eigenfunction expansion. And to discover more about that, we're going to discuss probability amplitudes as the first of 4 topics for today. So as a way of addressing the question of the meaning of these coefficients, the physical meaning, the mathematical meaning of these coefficients, let's ask the question, if I have some Hermitian operator A, we want to ask the question, what is the expectation value of this Hermitian operator A? Again, the context is we're going to have a particular wave function, which is giving us total knowledge regarding the quantum system. We're going to have some operator A associated with some observable, to use the language. We want to ask the question, how do we extract the expectation value of that particular operator A? How do we extract it from the wave function? So let's do that. And in answering that question, when we make use of the eigenfunction expansion, we'll learn something about these coefficients C. We'll also give those coefficients a name, which is a probability amplitude. So we ask the question, what is the expectation value of the operator A? Now let me use Dirac notation. In Dirac notation, this is the expectation value of the operator A. Whether or not we put a second bar here is immaterial. It means the same thing. This is a triple integral over all space of the first slot, starred, psi star, times A psi. We're using Dirac notation. So in Dirac notation, this wave function here can be written via its eigenfunction expansion with our eigenfunctions with our lowercase psi. Our operator A stays where it is, and our wave function psi can also be written via its eigenfunction expansion. At this point, I've made a mistake, a trap for first-time players, that this sum is the first sum and the second sum are summing over the integers n. Yep. So that n in some sense doesn't exist, in the sense that this expression is going to be independent of n. N is a dummy variable which is summed over. N is also being summed over here. The point is that when the sum is done, this has no little n dependence, and neither does this. The point being that I need to use a different index for each of these sums in order to do my accounting properly. To continue, I want to pull out these 2 sums, the sum over m and n. The numbers can also come out the front. This Cm gets starred because anything in the first slot is starred. Go back to the definition of Dirac notation if that point is not clear to you. This Cn can also come out the front. And what we'll be left with will be the open angular bracket, the psi n, sorry, the psi m, the A, and the psi n. So this is good. But this is an eigenfunction expansion. This object that I've just marked with an arrow is, by construction, by definition, an eigenfunction of the operator A. Yep. So when the operator A acts on the eigenfunction, it gives you the eigenvalue, which we'll call little a subscript n, that's a number, times the eigenfunction back again. Yep. So this number, this eigenvalue, can now come outside the Dirac bracket. Remember the bra and the ket, this can come outside. This number can come outside the Dirac bracket. So we do that. Sum over m, sum over n. We have our numbers, Cm star, Cn. An has come out. And we're left with the bracket of psi m and psi n. Yep. But let me write it down and then I'll rub it off in a moment. This bracket is 0 or 1. Remember that these eigenfunctions are orthonormal, which is a concatenation of orthogonal and normalized. This thing, like the dot product of two unit vectors, will only equal 1 if m equals n, and will be 0 otherwise. This is the Kronecker delta. Now, just as Dirac deltas render integrals trivial, so too Dirac deltas render sums trivial. Dirac deltas are to sums, Kronecker deltas are to sums what Dirac deltas are to integrals. The point is that this term will only be non-zero if m equals n. So this reduces our double sum to a single sum. We only keep terms where m and n are the same thing. Cm star Cm will be the magnitude of Cm squared. An will be Am, and the Kronecker delta is gone. So this is the final result of equation 157. As a special case, if we let the Hermitian operator A be a certain trivial operator, namely 1, then what we get is the expectation value of 1, right? And I'll leave you to show that the expectation value of 1 is indeed 1. All the eigenvalues of the operator 1 are just 1. So we get the following result. So this tells us something. This tells us that the sum of the magnitude squareds of the coefficients, again we're going to call them probability amplitudes, the Cm's, the complex numbers Cm, we're going to call probability amplitudes. The magnitude squareds of these objects are summed to 1, which just makes the point that these numbers, the magnitude of Cm squared, is the probability that you will measure the system to be in a particular eigenstate psi subscript m. And as we learned in the previous class, the coefficients, these probability amplitudes, are obtained by taking the mth eigenfunction and projecting it. Again, I'm using deliberately geometric language and projecting it onto the wave function or the wave function onto it. So we're henceforth going to call these things probability amplitudes. Let's now move on to unitary transformations. One key theme that I've mentioned many times is a rather fluffy sounding statement that the world exists independently of how you choose to do your physics, right? On the one hand, it's a fluffy statement. On the other hand, it's a profound statement. A vector exists independent of how you choose to coordinatize the space, whether it's with Cartesian coordinates or polar coordinates. An electron in a wave function in an atom in my finger exists and evolves quite happily, independently of how I choose to describe its physics. Just as there's no one way to coordinatize space, I could describe this in infinitely many different Cartesian coordinate systems, this vector. I could describe this vector infinitely many different ways in infinitely many different polar coordinate systems with different origins, and no particular way is privileged. By the way, that almost sounds like relativity, and that almost sounds like relativity. There is no privileged coordinate system. There is no privileged way to do quantum mechanics. There's infinitely many ways to represent a quantum system. Yep. So when I write down, for example, a wave function as a function of position and time, this is one way to describe a quantum system. We can say, let's represent the physical system with this wave function which obeys the Schrödinger equation. On the other hand, if we go to equation 15, we could have the momentum space representation of the wave function. It's equivalent to psi of RT. If you throw this into equation 15, you will synthesize the wave function via a Fourier integral. So this is a different way of representing the quantum system. What equation does it obey? I haven't told you, but you could write down an equation which governs this. There's two different ways of doing quantum physics. A third way would be we have our eigenfunction expansion. You give me this bunch of numbers, C subscript n at the bottom of the first board, and I'll construct via an eigenfunction expansion my wave function. So that set of numbers, Cn, can be stuffed into the eigenfunction expansion, 151, and used to synthesize the wave function. It could also be used to synthesize the momentum space representation of the wave function. The key point I'm making here is that there's infinitely many ways to represent quantum systems, just as there's infinite many different ways to represent a vector. Where do unitary transformations come in? Well, they come in as follows. Let me use the Dirac ket to denote this electron sitting on a cloud. And what I mean by that, as I meant previously, is that this is the electron existing, living, evolving in the atom in your fingertip. And it's not in a coordinate-free way, just like I hold the vector, and I don't yet give it a coordinate system. It's existing, it's happy, it's a vector. This is an electron in a wave function, or an electron in an atom doing its thing. I could choose to represent that system with a wave function, capital Psi, as a function of position and time. I could choose to represent it via a momentum space wave function. I could choose to represent it some other way, and there's infinitely many ways I could represent it, none of which are privileged. The question then arises, how do I translate or transform or change representation from one non-privileged representation to another? And the answer is with unitary transformations. Unitary transformations, you'll recall, are those whose Hermitian conjugate equals their inverse. They can be considered as good coordinate transformations in some sense. Information preserving in a loose sense. We'll make this more precise soon. The point is we're going to use unitary operators to transform from one non-privileged representation to another. To go backwards, you use the inverse operator, which is the same thing as a Hermitian conjugate. So we want to develop this stuff now in section 25 on unitary transformations. And again, think very strongly of the analogy with changes of coordinate systems with vectors. Just as an aside, I keep pushing this link between vectors and functions. The coefficients Cn in the eigenfunction expansion, 151, can be viewed very much as coordinates of a vector. This link between functions and vectors is very, very strong in quantum physics. So how do I change from one non-privileged representation to another? So let me just simplify this diagram on the left. I have one representation which I'm going to call psi. I'll have a new representation, psi tilde. In fact, let me call it psi with the hat on top. This is two different representations, and I want to use a unitary operator to go back and forth in this change of representation. So just to be more formal, in equation 159, I would say the new representation is obtained by taking the wave function in the old representation and applying a unitary operator to it. Fair enough. The next question is, we know that in this representation, the wave function, which is psi, will obey some equation. For example, if we were in the Schrödinger representation, which is what we've been implicitly in for most of the course, psi of RT, then this thing would obey the Schrödinger equation. But that begs the obvious question, what equation does this obey? Yeah? What equation does this obey? If your wave functions, the way that you represent the system, is changing from representation to representation, then your equations must also change. Again, as an analogue, Newton's equations of motion written in Cartesian coordinates look different if you move to polar coordinates, right? Similarly, Schrödinger's equation in the Schrödinger representation will change to somebody else's equation in somebody else's representation, right? So we need to ask the question, how do equations transform? And not just the governing equation which governs the spatio-temporal, or governs the evolution, sorry, of the wave function, but arbitrary equations. So for example, suppose I had let's call this the old representation, just to give it a name. Let me call this the old representation. And let me call this the new representation. Now what you call old and new, completely arbitrary, right? Nothing's privileged, but just for clarity, I'll speak of the old and the new. And suppose in the old representation I was to have some equation, some linear equation of the form, a linear operator acts on the wave function to give some other wave function, phi. Question, how does this equation of quantum physics in the old representation, how does it transform to the new representation? Good question, which we'll answer now. So we already know that the wave function in the new representation is obtained by applying the unitary operator u to the wave function as represented in the old representation. Similarly, for the new representation of phi, being related to the old representation of phi, this hat shouldn't be there. Old representation, act on it with unitary operator to give new representation. Now, if we take this equation here and pre-multiply by u dagger, yep, if we pre-multiply by u dagger, you'll get u dagger psi bar, u dagger u, right? But u dagger and u inverse are the same thing. Again, I speak of this as a dagger. I can also call it a Hermitian conjugate. I can also call it an adjoint. They all mean the same thing. U dagger act on the left side, gives this. U dagger on the right side, u dagger u, which is 1, comes the wave function back again. Why have I done this? Well, this equation tells me how to go from psi to psi hat. This equation tells me how to go from psi hat to psi. Yep. The two directions of the arrows. Similarly here, we'll obtain that phi equals u dagger phi hat. Now we know how wave functions transform. They transform according to this boxed equation. The question I want to address now is, how do the operators transform? Yep. Now, linear algebra occurs so often. What I'm about to do is not peculiar to quantum physics. It's called a similarity transformation. It's called a similarity transformation in linear algebra. And I'm trying to think of an example. So let's consider this change of coordinate system for a vector. Now I can take an active perspective, in which case I would rotate the vector rather than the coordinate system. I could also take a passive perspective on coordinate transformations, where I change the coordinate system rather than the vector. So if I have an XYZ coordinate system, I could do this and call that a change of coordinate system. Alternatively, I could be arrogant and say, no, that's a coordinate system, but the whole world rotates. Let me take the passive perspective. So I have an XYZ coordinate system nailed to my head, or sorry, sticky tape to my head, and I do this, right? I've changed my coordinate system from this to this. Now let's consider a particular operation. For example, stretch your vector by a factor of 2 in this direction. There's an operation. Stretch the vector by a factor of 2 in this direction. So I apply my operator, and this miraculously doubles in size. But now I'm going to change my coordinate system, right? I've changed my coordinate system. So how do I apply a stretch in this direction? What I would do, right? I've changed my coordinate system, here I am, and I want to stretch this vector in that direction. What I would do, or one thing I could do, is the following. Go back to where I was, stretch, and then go back to the original. So this is my new coordinate system, right? This is the coordinate system I want to use, but I want to take my operator and ask how the operator in this system says double the length of the vector in this direction. How do I transform that operator to my new system? Well, what I do, I cheat. I say, look, too complicated, too hard. I'm just going to do this, stretch, and then go back again. Yep. In other words, I need to do the inverse operation, stretch, and then go back to my coordinate system. Now that's truly hand-waving and vague. I regret giving that crap explanation, but it's going to emerge out of the mathematics, right? The mathematics will tell us in the precise language what I just explained by a terrible analogy. All right. So asking the question, how do operators transform under the change of representation? So we take our equation, which converts psi hat into psi. So just one second. Yep. So we have our equation. Operator acts on wave function to give new wave function in old representation. Instead of psi, I'm going to have u dagger psi hat, u dagger psi hat. Instead of phi, I'm going to have u dagger phi hat. Again, we want to ask the question, how does psi transform? Now, I know what equation I want. I want the transformed version of psi acts on the transformed version of the wave function to give the transformed version of the wave function. That's what I want, right? I want to just change the representation of everything from the old representation without hats to the new representation with hats. So that's what I want. I know my answer. And I need to massage this into the form of the answer I want. So I don't like this u dagger. I'm going to get rid of it by pre-multiplying by u, because I know that since u dagger equals u inverse, which is the very definition of a unitary operator, that this right-hand side is now what I want, phi hat. This bit here is already what I want. So I stare at that equation and I'll will it to be what I want. Yep. This thing I'm underlining in purple is the new representation of the operator. The new representation of the operator is u dagger. Again, if I was teaching linear algebra, I'd call this a similarity transformation. Remember also that operators act from right to left. We can imagine a wave function on the right-hand side, a wave function on the right-hand side. And it acts from right to left because this wave function, which is implicitly sitting at the point marked with an arrow, is hit by this operator first, the inverse of the transformation. Right? Then you apply the operator, then you go back to the old coordinate system. Again, that was my vague analogy, but this is the mathematics telling us precisely how to transform our operators. Yep. So when you have your unitary change of representation, which can change psi into psi hat, which can change psi into psi hat as given by this Boxed equation, then the operators themselves must transform from the old to the new representation via this similarity transformation. Exercise 46 looks like the most boring exercise in the whole course. In fact, it's the most profound exercise in the whole course. So before I quickly go through it, let me make the point. Go to the library, or better still, go on the internet, we live in the 21st century, and look up any text on supersymmetry. And I guarantee that the very first thing that they'll give you will be commutation relations. And you might think to yourself, why the hell is the first thing in any supersymmetry textbook commutation relations? And that's because people know about exercise 46. Very, very profound. It looks trivial, and mathematically it is trivial. A high school student could do it, but this is absolutely the most profound result in the whole course. Suppose I'm in the old representation and I have two linear operators A and B, and suppose they obey some commutation relation. The commutator of A and B equals some complex number C. Question, let's change from the old to the new representation. A now becomes A hat and B now becomes B hat. Fair enough. What's that commutator? Well, you work it through and what you'll get will be exactly the same number C. That looks boring. It's not. It's profound. And it's profound for the following reason. This is the wave function existing on its cloud, independently of how we choose to do quantum mechanics. This is one of infinitely many different ways of representing that system. And we'll learn 4 or 5 different ways of representing a system in this course. This is another way of representing the system. We can go back and forth between these, any two of infinitely many representations using our unitary transformations. But this thing will obey some equation. In the Schrodinger representation, it'll be the Schrodinger equation. In the Heisenberg representation, it'll be the Heisenberg equation. In the Dirac representation, it'll be the Heisenberg-Dirac equation, and so on. In some other representation, you'll have some different way of describing the system and some different equations. But if, and this is a key point, this is a profundity, if you work in terms of commutation relations, then you're doing what you would call representation-free quantum physics. The reason that supersymmetry texts hit you with commutator algebra on their first page, or their first key equations, is because when you work in terms of commutation relations, you're doing something that seems almost incredible in the literal sense of the term. You can actually do quantum mechanics without going to a particular representation, while never actually writing down a particular wave function. And you think about that, right? You have nothing but pure algebra. I mean, the ancient Greeks would be rapt, right? You have nothing but algebra, the algebra of the commutation relations, and that's it. You'd also know that the operators are Hermitian, and that's all, nothing else. It seems almost too rarefied to do quantum physics with nothing but algebra, the algebra of Hermitian operators. But you can do calculations this way. And there's a section of the course which is optional, which I won't go through, section 28, actually calculates the energy levels of the hydrogen atom. Remember we went through all that pain working out the energy levels of the hydrogen atom? We wrote down the Schrodinger equation, we put it in polar coordinates, we did separation of variables, we pulled all these fancy tricks with power series solutions, and we ended up with a formula for the energy levels of the hydrogen atom. If you're doing representation-free quantum mechanics, you would have the commutators, energy momentum commutator, position momentum commutator, and that's it. And you'd know that the commutators were Hermitian. And by the way, since you have no representation, you don't have any functions of position and time. And if you had no functions of position, for example, then you'd have no grad squareds, all those bloody derivatives and vector analysis. If you're not even stooping down to representing the wave function in a particular way, then you have no differential equations. This is a world of pure algebra, right? You have no differential equations because you have no functions of position. Because even writing down a function of position is too much like representation, right? If you do representation-free quantum mechanics, you work in terms of commutator algebra, of Hermitian operators, and that's it. And you can work out a surprising amount of stuff. For example, optional section 28 works out energy levels of hydrogen atom without writing down any differential equations. You have nothing but algebra, no DEs. I'm repeating myself, but that's because it's cool. Exercise 46 looks boring, where you prove that commutation relations are independent of representation, but this is actually one of the most profound results for the course, and it's at this point that the course makes closest contact with extremely modern advances such as supersymmetry. All right, I'll rabbit it on and off. Yes. Section 26. So I've alluded several times to the profound connection between linear algebra of vectors and linear differential equations, between representing wave functions as functions of position and time and representing wave functions as vectors in some sense. So this very powerful connection between the theory of vectors, which is linear algebra, and the theory of linear differential equations. So let's get a bit closer to this. Let's explore in more detail by introducing a new representation of quantum physics called the matrix representation. And historically, when Schrodinger was writing down the Schrodinger equation, there was other physicists, Heisenberg, Born and Jordan. Heisenberg, Born and Jordan developed a different theory of quantum physics. And this different theory of quantum physics used utterly different language. Instead of speaking of wave functions, they spoke of column vectors. Instead of speaking of linear operators, they instead spoke of matrices. Matrices act on column vectors to give new column vectors. Linear operators act on wave functions to give new wave functions. Instead of having the Schrodinger equation, which governs how wave functions evolve, they instead had matrix equations of matrix mechanics, which govern how these vectors evolved. And this, in retrospect, is just two different ways of doing quantum physics. They were developed separately, The proponents, by the way, did not like each other, and they certainly did not like one another's theories, but it was ultimately shown that these two theories were equivalent. So it's a special case of this diagram is that psi is wave mechanics with the language of psi of RT's in Schrödinger equation, and we want our second representation as a special case to be matrix mechanics, which is the topic of this section. And what we're going to do is to go from wave mechanics to matrix mechanics via a suitable unitary transformation. And the key here is going to be our eigenfunction expansion. So let's do it. Operator acts on wave function to give new wave function. So this is now in the Schrödinger representation. Psi is a Schrödinger wave function. A is a linear operator, which turns the wave function phi, psi, into some new wave function phi. Next, I want to represent these objects via eigenfunction expansions. Yep, so psi we represent as an eigenfunction expansion with the notation I've already defined, and similarly with phi. Now I'll sum this one over n, because I'm careful about sums over m versus sums over n, for reasons already explained. My coefficients, I'll give them a different name. Complex coefficients I'll call d subscript n, but the same eigenfunctions. I can build two different brick walls out of the same set of bricks. I'm building two different wave functions out of the same set of bricks, the same complete set of eigenfunctions of some particular linear operator. Now, as soon as we do this, we're representing our wave functions via sets of numbers, which could be viewed as components of an infinite dimensional vector. So the eigenfunction expansion has implicit in it the idea of thinking about functions and somehow mapping functions onto vectors. We want to ask the question now, how does this equation change? If psi is a vector and phi is a vector in the sense I've described, then the linear Hermitian operator A is going to become a matrix. The matrix acts on column vector to give a new column vector. Question, what is that matrix? When we do that, we'll have the matrix representation of this Schrödinger picture equation. So let's do it. We take our equation, and we're just going to substitute in our eigenfunction expansion operator, acts on wave function, to give new wave function. This is equation 168. Next thing, I'm going to bring this A inside the sum. It can jump past the sum. It can also jump past the coefficients. So I'm going to put the A in here. So the A has come inside the sum, the C subscript n, and then the operator A. Good. Next, I want to pre-multiply both sides by psi p star, and to integrate over all space. So let me just write the equation again, leaving judicious gap. So I've done nothing more than rewrite the equation, and now what I want to do is to pre-multiply by psi p star, which is a particular member of this complete set of eigenfunctions. This is our complete set of eigenfunctions. I want a particular member of this set, which I'm going to call psi p. So I'm going to pre-multiply both sides by psi p star and integrate over all space. Now, in Dirac notation, that will be written as follows. You can write it out longhand if you want. Again, I've pre-multiplied both sides by psi p star. The star is implicit in being in the left hand of the Dirac slot, and integrated over all space. So we have this expression here. What I'm working towards is the question, how do I represent this as a matrix? And I'm going to answer that question by writing down the matrix, which corresponds to the linear operator A. All right. Again, sometimes when you work with very general things, things become simple. I mean, this is a triple integral over all space, right? but this is an arbitrary set of wave functions, of eigenfunctions, sorry, an arbitrary complete set. A is an arbitrary linear operator, and precisely because they're arbitrary, you can't really work stuff out. You don't go into first year and second year mode of working out mad integrals, because these are arbitrary, therefore you can't do the integrals. So I look at the thing that's underlined in yellow, and I ask the question, what is it? And the answer is, it's a number. How do I calculate that number? I don't know, because A is an arbitrary linear Hermitian operator, and psi m is a complete set of eigenfunctions, but otherwise arbitrary, of that linear operator A. So this thing I'm underlined in yellow is a number, which certainly depends on the operator A, and also will depend on the integers p and m. So I'm doing nothing profound here, I'm just giving this object a name. I'm calling it A subscript pm. Now this set of numbers, and p and m are integers, full infinite set of integers. This can be viewed as the elements of a matrix. Question, is it the matrix representation of this linear operator? The answer is yes, but we need to show that. All right, so I'm just giving this a name. I'm calling it A subscript pm. So my equation now becomes the sum over m. Now I know in quantum physics we get a bit paranoid about order in which things appear. This is a number, this thing is a number. The order in which we multiply ordinary numbers is immaterial, and so the Cm and the A subscript Pm can certainly be interchanged in order. The right-hand side, this is an orthogonal and normalised set of eigenfunctions. This thing is only non-zero when p equals n, which kills off the sum, and you just get d subscript p. So we began with this equation in the Schrödinger representation with its language of wave functions and Schrödinger equations, and we now have this equation here. This is the column vector. This is the set of numbers which describe the wave function psi. Yeah. Ditto for d subscript p as far as phi is concerned. So this is a way of representing psi and phi respectively. The equation was A psi equals phi. The equation is this thing here. But this is nothing more than a matrix equation, and this is where the connection between the theory of matrices acting on vectors to give new vectors connects. Yep. If we arrange the set of APMs in a matrix, it'll be an infinitely large matrix, that's fine. This is our infinitely large matrix, acts on our column vectors, whose components are C1, C2, etc., to give a new column vector. So we just transformed from an equation, an arbitrary linear equation, involving a linear Hermitian operator in the Schrödinger picture, with the wave function obeying the Schrödinger equation. We've transformed to a new way of doing quantum physics, in which linear operators are represented by infinite dimensional matrices, and wave functions are represented by infinitely large column vectors. So when I use a term such as function space, you'll think about vector spaces, right? In linear algebra, we did all that stuff with vector spaces in second year. We can also think of functions as vectors, and if vectors live in vector spaces and functions are vectors in this context, then functions live in function spaces. I love functional analysis. I'd love to talk about functional analysis, about which this is the tip of the iceberg, but I have no time. So please look up functional analysis. It's very, very cool. We give these things a name, by the way, these APMs. Since they're the elements of a matrix, so these APMs, which I'll just remind you, according to this, are obtained by taking this Dirac bracket of the pth eigenfunction, the linear operator A, and the nth eigenfunction. These things, because they're the elements of a matrix, are called, somewhat prosaically, matrix elements. If I was talking to you about the quantum theory of scattering, where you take targets such as atoms in the Large Hadron or elements in the Large Hadron Collider, and you scatter high energy particles from them. The theory of matrix elements in the form I've given occupies a hugely important place. So if you look up the quantum theory of scattering and you look up the term matrix elements, then you'll find that permeates the quantum theory of scattering. Again, that's a subject for a later year. In fact, it's covered in honours. I want to go back now to this idea of the electron in the cloud. And to speak of the state vector. Because in many respects what we're doing is we're eroding the primacy of the Schrödinger way of doing things. At the beginning of the course it was all about Schrödinger wave functions and Schrödinger equation. But I've been banging on about the idea that there's infinitely many ways to do quantum physics. We can represent a wave function in the Schrödinger picture. We can represent a wave function in its momentum space representation. We can represent it as a column vector in the theory of matrix mechanics, which is section 26. Or we could represent it in infinitely many other ways. But again, the electron exists independently of how we choose to coordinatise it. So I know that I was writing this ket psi inside a cloud to loosely represent the idea that this is trying to denote the wave function of the electron existing in a representation-free way. But if you pick up an arbitrary quantum book, you will not see clouds drawn. They'll just draw this ket like this. And when the ket, as in Dirac bracket ket, when this ket is just written as a standalone way, it's understood, it's implicit, that this is a representation-free quantum mechanics. When, for example, you write psi of RT, this is a function of position and time, which obeys a differential equation, the Schrödinger equation, etc. This is quantum mechanics in a particular representation, but when you write the wave function in this way, it's understood to be representation-free. And again, this connection between linear algebra and functions, we speak of this function as a state vector. Just as this vector exists independent of the coordinate system we choose, so too this wave function, when written in this way and called the state vector, is writing it down in a representation-free way. Section 27, I'm not going to go through it and it's not examinable. I actually go through this in detail in my honours classes. The key point here is that you can do, because of exercise 46, because of the fact that commutators are independent of representation, you can actually do meaningful quantum calculations purely within the setting of the state vector in a representation-free way. Again, that sounds almost too good to be true, but section 28 will enlighten you as to how this works. It's a very rarefied atmosphere. Again, you have no functions, so you have no differential equations. Hooray. You have no functions, so you have no integrals. Hooray. You have nothing but algebra and a very, very, very limited toolkit. So in a sense, you need to switch off your sophistication and just work with pure algebra if you choose to work through section 28, which I encourage you to do so. I'll stop there. Just as a reminder, your assignments are due today. Please hand them in to the third year physics labs. Anytime today, there'll be a pigeonhole for the assignments. Great talking to you as always, and until next time.